So I'm not going to go in the way how the textbooks deal the theoretical aspects. Let us try to intuitively and mathematically figure out what exactly we mean by current source or current mirror through with the help of a simple small signal modeling. We'll do the small signal modeling, and then we'll arrive at a particular observations, and based on those observations, possibly in the upcoming sessions, we'll try to simulate certain aspects on these particular things. Okay, so basically, as you know, current mirror, which basically we often use the term current source and current mirror repeatedly inversely. So it is basically one most important aspects of your VLSI or semiconductor physics or analog circuit design, where we try to use it very frequently. And the reason being, if you observe over here, whenever we need any particular current in our entire circuitry, we never go and get it from the actual current sources. Rather, we try to generate the currents required by us as per the need, based on what exactly is the requirement. So basically, let's say I want to ensure that I want to have the current, or let's say I want to generate a current of 100 microampere, and I also need 200 microampere of current, and at some point of time I need 1 milliampere of current. So I cannot keep on using many different current sources. So what I'll do, I'll use a simple current mirror, and I'll from that current mirror I obtain the mirroring action of what is the value, and from there I use those particular values of current in our entire circuitry. So let's try to get into this particular thing. So let's say I have, this is my, here is my I out, which is again a combination of DC plus AC. Okay, let's see. I have this particular circuitry. I'm getting it very specific to this particular circuitry, and later we'll try to figure out various versions of current mirrors and current sources. So what exactly, in a simple terms, the current mirror? Current mirror is basically, like I told, it is that particular circuit which is going to mimic or mirror the reference current, which you can see in this particular left side, and get it across the right side, which is in the Q2. Because your VGS is connected together, and since this Q1 is in always in the diode connected format, what does that mean literally here is this Q1 will be biased in the saturation region, and because Q1 is biased in the saturation region, see here Q1 is diode connected. Why? Because see here, the GSD, if you observe, the VDS greater than VGS minus VT, this condition is always satisfied for Q1, hence it is always in saturation region. Now, because it is always in the saturation region, what does that mean in turn? That also mean that it is going to have a constant current. So constant current in Q1, and because gate of Q1 and Q2 are tied together, what does that in turn mean? So I mean VGS2 is equal to VGS1, and because Q1 is in already saturation, and due to VGS1 and VGS2 being the same, whatever the condition that applied for Q1, the same condition will be applicable for Q2. And because for a particular value of VGS, see, what does this mean? This means since Q1 is in saturation for particular VGS, and the same VGS is applied to Q2. Therefore, Q2 will also be in saturation, and hence a constant current would be replicated in the I outside of the Q2. So basically, whatever is my reference current I have, let's say if I have 1 microampere, the same 1 microampere current will be replicated in the I outside. So this one particular aspect will try to simulate in the subsequent session. That is one thing. Now, coming to what exactly I want to deal over here is, now I came to know that this is my current mirror, because the current is mirrored in Q2. Whatever the current is there in the Q1, it will be mirrored in Q2. And now we'll try to understand certain characteristics of this current mirror. So basically, what would be my input resistance, what would be my output resistance, and what is my gain, how do I calculate the current gain, because I say this is a current source, right? So basically, why I call it as a current source and current mirror invariably, because see, this from this I reference current source, the same current will be mirrored over here, and henceforth you can utilize this current in any part of the circuitry. So I can connect this current IOT to any part of the circuitry. That means that now this IOT is acting as a current source for me. So IOT would invariably behaving as a current source, generating a I reference value of current. If you change I reference, the IOT will also change. And how do I, by keeping I reference equal to, let's say 100 microampere, can I generate 50 microampere current in the IOT? That can also be done. So I can keep on changing the parameters of Q2 and Q1, and invariably I can obtain various different currents without touching I reference. So what are those things and how can I do those things? Let's try to understand that. Now, before that, why have we written here capital I1 and small I1? So this is basically a DC and this is basically an AC. Remember, whenever we try to generate the currents, or whenever we try to play around with the current and voltage signals in our entire MOSFET related circuit, you should ensure that you are mentioning both AC and DC. It is only during your AC analysis you short the DC sources, and in the DC analysis you ignore the AC sources. But invariably, the current or the signal or voltage values, whatever you are seeing, it is a combination of AC and DC, because there will be always two sets of voltages and currents that would be there in your entire MOSFET circuitry. The DC sources would be acting as your biasing based sources, and AC sources basically will be acting as your actual inputs and output sources. So here, from this particular thing, now let us try to, I'll do one thing. What I'll do is I'll just copy this and let me paste it over here. Yeah. So now from here, let's try to reanalyze our entire thing. So let's try to understand with the small signal model. Remember, this small signal model is the one particular tool that helps us to break down the entire complicated circuit and understand the scenario in its most simplified form. Okay, so let me draw the small signal model for Q1 and Q2 side by side, and then let's try to figure out what is going to happen. Now, because there is a current that is coming from this VDD, and here it is a small signal model, I am considering only AC sources. So DC sources are, I can say it is being grounded. So I cannot consider DC sources. I'll be only considering the AC. So I can just first start with my simple I1 as my this current source. And as you know, the MOSFET can be represented in its simplified small signal model with the help of a simple resistance R0 and a dependent current source of value GM times VGS. So this is basically your representation. And now, because I have two MOSFETs, let me rename my RO as RO1 and GM as GM1. And let me, since VG is already same, it is connected, the same VG is connected. So I am going to keep VGS as VGS only. And because drain and gate are shorted, so that means this terminal is together is my drain and drain and gate. So this is with respect to Q1. Now on the same line, let me draw the small signal model for Q2. Again, I need to mention a simple current, dependent current source of value GM2 times VGS and with a finite output resistance, which indicates the channel length modulation. There you go. So this is basically the small signal modeling of this entire current source. So now when I have this particular thing, let me just try to bifurcate this with respect to Q2. So let me try to bifurcate this entire small signal model in terms of something else. So basically, we know that from the simple first principles Ohm's law, V is equal to IR. So if I consider VGS is equal to, and what is my I here? So basically this is my current source, isn't it? Here I is my current source, and what is the value of I here? So basically this is your ID. Okay, so that ID is represented by the term GM1 times VGS. So here let me let VGS is equal to ID times R. So that becomes VGS equal to ID is represented by the term GM1 times VGS and R. And by this VGS cancels out, and this can be written as 1 equal to GM1 times R, or I can simply write R is equal to 1 by GM1. So what does that mean? I can replace this entire current source ID, dependent current source ID, with a simple resistance of value 1 by GM. That is basically the meaning. So I can replace ID is equal to GM1 VGS with R, which having a value of 1 by GM1. So let me just replace that and redraw this entire structure. So instead of redrawing, let me just copy this same structure over here. So let me just copy this over here. Yeah. And let me just replace this entire thing with the help of a simple resistor value 1 by GM1. There you go. Rest all things I'm not going to touch. So that I'm going to keep it as it is. Later at the end of this entire session, you'll come to know why I did all these things, all this entire thing. Okay, and of course there will be plus minus. Here will be your VGS. That voltage will be applied because this is gate and this is your source. Whatever the voltage that is there, that will be your VGS that will be present over here. So let me just mention that also. So here will be your VGS. That anyhow will be there. No need to mention this anyhow, but still let me just mention that also. Okay, so this is basically my small signal model, a modified one. Now once I get to know all these things, it becomes easy for me to calculate the other characteristics, other properties of my current source. Here, looking from the input side, I can calculate what will be the input resistance, and looking from the output side, I can calculate what is my output resistance. So based on that particular thing, I can easily say that R in is nothing but RO1 parallel 1 over GM1. Now you got to know why I replaced this with a resistance, because to calculate the input resistance, if I replace that current dependent current source with a simple resistance, I'll be able to calculate the input resistance, and I can club the entire input resistance together in the form of this. And now, because your what I can say, RO1 is very large, therefore Rin is equal to just 1 over GM1. So this is very, very important. And later down the lane, when we try to visualize the amplifiers, you'll come to know what should be the input and output resistance, and the relevance of input and output resistance. But right now, this is the input resistance of the current source which we generated through the principle of current mirroring. Now on the same line, what is my R out? R out is basically, if I look from the output side here, this is my output side, only RO2 is visible, so there is no other resistance, so it is simply RO2. That means the interpretation here is, see what is the interpretation. See, for current sources, we are very keen on the output resistance. R out of any current source must be large, therefore, R out is equal to RO2 must be large. And we have already seen through the simulation how do we calculate the finite output resistance. So that means henceforth, if you calculate any MOSFET's small signal, or if you calculate the MOSFET's R0, which is basically the finite output resistance, that itself can be considered as the output resistance if I am using that MOSFET to build a current source. So basically our design started that way. So we started off with a simple MOSFET characterizing its drain current and VGS with respect to VGS and VDS, and then we plotted the graphs, and then we took the derivative of those things and we figured out what is the finite output resistance, which is my small R0. Now from this entire exercise we can summarize that the small R0 can itself be utilized as a the output resistance whenever we are going to use this MOSFET in building the current sources. So that is one thing. So this is basically R out, and this R out should be very, very large. And now you also know that how do we calculate R out, or basically a small signal R0. R0 is basically, we have already seen how do we calculate R0. R0 is basically we have to plot ID versus VDS graph, and with the help of ID versus VDS graph, so basically what is, let me just and note here is R0 is basically, what is that? Dou VDS by dou ID. That is how do we do that? Plot ID versus VDS graph and take the derivative. So we get dou ID by dou VD, and then take reciprocal of it. So this is what we have done it in our entire cadence exercise. So that same thing you do, you get the R out. So always remember, R out is totally different than R naught. R out is a circuit parameter, and R naught, small R naught, is a device parameter. Okay, so that is basically the intent of this particular small signal analysis. Okay, now once we know this thing, now let us try to understand what is the current gain, because we say that we have designed the current source, so we should have some current gain, isn't it? So Let's just copy the same circuit over here, and then yeah, let me just copy this circuit and keep it over here, and let's try to find the current gain. Current gain is basically I out by I in, and here I out is here, which is over here. So basically I can write current gain can be written as AI is equal to I out by I in. And in this case, what is your I out? It is basically I2 by I1, right? Or basically I naught. I can say it as I naught also. Or if I consider I2 is equal to I naught, because it is at the output side. So now let me just represent these things. So basically, what is I2? I2 we have already mentioned over here through its small signal modeling. What is I2? This is your I2, GM2 times VGS. So basically, this is your, I can say I2, that is basically GM2 times VGS. So let me just write it over here, GM2 times VGS. And what is your I1? Let me just keep it as it is I1. Okay. From that small signal model, if we observe, what is the observation we can make? See, R naught is very large, always remember. Basically R naught will be large, and here R naught 1 is very large, and that's what you quoted over here. It is very large, and because R naught 1 is very large, entire current, the small I1 current from the input side, whatever it is coming, it will not flow through R naught. It will all flow through the 1 by GM1. So basically I can say, because R naught 1 is very large, all input current will flow through which thing? It will flow through GM1 times VGS. Let's see over here. Let's not look over here. We have to look from the original one. Yeah. R01 is very large. So all the entire current will flow through GM1. Basically, I1 is nothing but, see here I can say, as per the current KCL, current leaving this node, which will bifurcate into RO1 and ID. So basically I1 is nothing but current through RO1 and current through ID. And because R1 is very large, all the current will flow through this particular wing. So let me mention this as figure 1, and I'll refer that over here. Okay. So everything will flow through GM1 times VGS. So that means I can say I1, no current will flow through R0. So I1 is now is equal to GM1 times VGS, because simple KCL, like I told over here, I1 is equal to here. See, I1 is equal to current through RO1 plus current through GM1 times VGS. But because this is very large, I can say I1 is directly equal to GM1 times VGS. So I can, that's what I'm writing over here. I1 is equal to GM1 times VGS. So with that, yeah, with that, AI, it is I2 by I1 is equal to GM2 times, sorry, which is basically GM2 times V. VGS divided by I1. Now I can write it as GM2 times VGS whole divided by what is I1? GM1 times VGS, isn't it? I1 is GM2 times VGS. I1 is basically now again GM1 times VGS. So that way I can say that this VGS cancels. And what is my gain? Yeah, I can be represented as GM2 by GM1. And that's how why your transconductance plays a very crucial role in identifying or in understanding your entire thing. So even or what I can even this can be also solved this way. uh, a I is equal to I2 by I1, and I can represent this. Let me keep I2 is what, GM2 times VGS, and I'll keep it as I1. And from this VGS here, from this VGS, let me take it as equation 1. From 1, VGS is equal to I1 by GM1. So that would give you AI is equal to I2 by I1 is equal to, in the place of VGS, just substitute I1 by GM1, and below will be I1, and this will cancel out, and again you are going to get the GM2 by GM1 only, which is your current gain. And that's the reason why I insisted always to go and obtain and figure out how we obtain this GM is very, very important. And we now know the formula for GM also. We know that simply what is GM can be written as mu1 C ox W by L VOV. That's my formula. So therefore I can now write current gain is equal to GM2 by GM1. Now, because 2 means transistor number 2, mu and Cox are the common things. W by L of transistor number 2. Overdrive voltage is also common, because what is overdrive voltage? It is VGS minus VT, and VGS is common over here. That won't change. And same over here, mu and Cox is common for both transistor. W by L of 1 times VOV. So this makes that our entire things would cancel out except W by L of 2 divided by W by L of 1. So that's my current gain. So that's the beauty of your entire current source from the current mirroring action.